Great. Now, important properties of relations. So as we've defined them, they are very general. They satisfy almost no properties in general. But here are some definitions of some properties that some relations satisfy, which are very important for working with them. So let R be a relation on a set A. So just to reiterate the definition, R is simply a subset of A cross A. We say that R is reflexive if A comma A is in the relation for any element of A. So it's reflexive if every element of your set is related to itself. So let's, for example, what are the examples that we did before? So divisibility, we do have A divides A. That is true. So that is a reflexive relation. Congruence, let's see, A congruent to A mod 5. That is also true. So that's reflexive. And less than or equal to, A is less than or equal to A, also true. So these are all reflexive. As a non-example, less than is not reflexive because a number is not less than itself. I'll put quotes here. So that is what it means to be reflexive. The relation is symmetric if we have some pair A comma B in R, if and only if the swapped pair B comma A is in R. So symmetric means, maybe what it suggests from the name, means the order doesn't matter for measuring this relationship. If they're related one way, then they're related the other way. And there is a related definition, anti-symmetric, which means if you have A comma B and B comma A, then A must equal B. So anti-symmetric, what is anti saying? It's essentially saying that you can only have one of these two pairs, unless, except if A and B are the same. But basically, what is the contrapositive of this statement? It's that if A is different from B, then only one at most of these pairs is in your relation. So anti-symmetric means, it's one way of saying what is the opposite of being symmetric. So which of the examples we've seen fall into these categories? So congruence is symmetric. This is just to say that A is congruent to B mod 5, if and only if B is congruent to A mod 5. That's certainly true. But these other ones are not. So less than equal is not symmetric. In fact, it is anti-symmetric. because if x is less than or equal to y, and y is less than or equal to x, well, that means that x must equal y. And that is exactly our definition of anti-symmetric. Let me put in parentheses that the less than, strictly less than relation is vacuously anti-symmetric. And if you remember what vacuous generally means, it's vacuously anti-symmetric because this thing is just never true. So the property is satisfied because an implication that starts with a false thing is always vacuously true. So it's vacuously anti-symmetric because you never have x less than y and y less than x. This is impossible, so it's satisfied. And finally, divisibility is neither symmetric nor anti-symmetric, which is certainly possible, because in the case of divisibility, if A divides B and B divides A, then B must be plus or minus A. So it doesn't nail it down to A exactly, it's just plus or minus A. But for example, if you restricted yourself to the positive integers, then divisibility would be anti-symmetric. Very good. So the last important property, R, is transitive. If A and B is in R, and BC is in R, implies AC is in R. So basically, transitivity is saying that your relation is compatible with chaining relations together. So A is related to B is related to C. That tells you that A is related to C. That's what this definition is saying. So, in fact, all of the examples that we've seen so far are transitive. Divisibility, because if A divides B and B divides C, then A divides C. That is true. Congruence. If A is congruent to B and B is congruent to C, then A must be congruent to C. Less than equal is transitive, because if x is less than equal to y is less than equal to z, then x is less than equal to z. And less than, same reason, all transitive. Let me just write down as an example, A divides B and B divides C implies A divides C. That's the kind of thing that you need to check that this is transitive. But let's see an example of something that is not transitive. So let's define a sort of neighbor relation on Z by saying R, let's write it in this way again. When is A related to B? A is related to B when B is A plus or minus 1. So the things that are related to A are its neighbor, one to the left and one to the right. This is a perfectly good relation. It is symmetric, I think. It is not reflexive, and it is not transitive. Intuitively, because it relies on some sort of like close proximity. So it will not survive when you go further and further from the source, which is what transitivity requires. But to give an example, 3, 4, is in R because they are neighbors. And 4, 5 is in R, they are neighbors. But we cannot chain these together. 3, 5 is not in R because they are not neighbors.